Good morning, everyone. Welcome to Brandforsk and our result webinar presenting the research project Studies on Environmentally Friendly Flame Retardants for Cellulose-Based Materials. My name is Mattias Delin. I'm the Research Director at Brandforsk, the Swedish Fire Research Foundation. And this project will be presented by Anna-Karin Larsson and Anitam Patra from Luleå University of Technology. Good morning, welcome.
Good morning.
Morning.
Thanks for the invitation.
Very welcome. So Anna-Karin, who are you?
I'm an associate professor in chemistry of interfaces at the Division of Chemical Engineering at the university. So I'm also teaching fire engineering students in risk and fire chemistry. So that's how I started this flame retardant projects. So both Anitam and me are quite new. We have only worked with this a couple of years, thanks to Brandforsk, who gave us money to start this. So we are excited to learn more from any experts who are in the audience today.
Oh, excellent, excellent. So you're very welcome, and welcome Anitam.
I am Anitam.
Who are you?
I am senior researcher in Luleå University Chemical Engineering Division. So me and Anna-Karin work together, and I am also co-teacher in the fire engineering course. Yeah,
Excellent, thank you. And this is your second stage of
exactly,
this research. You've done stage one, and we presented that about a year ago, and now you have reached a new level on that. And you will guide us today through your process of building an effective molecule for flame retardants of cotton, and you will also show us how your molecule reacts to heat and the mechanism that serves fire protection. And a word of advice to the audience from me is to stay focused through this presentation and this journey. And at least I had a wow experience on flame retardants chemistry, and maybe you will have that too. I think that it's really interesting to hear Anna-Karin and Anitam explain the very interesting chemistry behind what happens in this. So we'll see more of you soon, Anna-Karin and Anitam. Thank you. A few words about us at Brandforsk. We have a vision, a fire-safe society built on knowledge. We develop and communicate knowledge, mostly research, to limit the negative consequences of fire in the society. We started in 1979, and since 2 years back, we are a foundation. We have supporting organizations that fund everything that we do. This makes us a collaboration between many parts in the society. And the funding so far this year is about 650,000 euro. And of course, we use our money to fund research like Anna-Karin and Anitam's work, for example. And we also work a lot with communicating research. We also have a research school for practicing fire safety engineers in fire services. They are part-time PhD students beside their work in the fire service. And we have scholarships for students. And these are our supporting organizations this year, and it's really thanks to them that we can do this and have this webinar, for example, today, and also that Anitam and Anna-Karin can do their research. And as I said, funding so far this year is about 650,000 euro, and please support us if you are not already doing that. The program today, after this short introduction, we'll get a presentation of the project. It's about half an hour. And after that, there will be time for questions and discussions. And please write your questions in the Q&A. So let's now go to the presentation.
Yes, thank you for this invitation to the webinar. We will present our results from the project about environmentally friendly flame retardants for cellulose-based materials. This is a continuation of the project that we had a few years back, where we looked at one flame retardant that we have developed on cotton and wood. But now we have tried to improve this flame retardant. So we are focusing on cotton in this project. So my name is Anna-Karin, and I'm an associate professor in chemistry of interfaces, and my co-worker Anotam Patra is senior lecturer in the same group. So you will meet him soon. And we want to acknowledge many people working with us. And first, we want to also acknowledge Brandforsk for the financial support and Francis for all the help with the administration. We have had a project panel group, 5 members who have been very useful for us in this project: Matthias, Anders, Robert, Thomas, and Leif. We have also had some collaborators at LTU, Luleå University of Technology. We have our fire colleagues, Mikael Furst and Alexandra Byström. And we have had Sushandra Sar in our own group, and Alexis, who has been working with us as a bachelor student. And we also have had help from Tobias Sparman at the NMR Center at Umeå University. So the background of this project is to have a safe environment at home. So textiles made from natural fibers have become very popular, and cellulose is the most common source of those natural fibers. So we have them in cotton, linen, viscose, lyocell, and they are renewable resources and considered sustainable. But there is one problem: they can all easily catch fire. So for a fire to happen, we need 4 components. This is called the fire tetrahedron. So we need heat to start the combustion reaction. So when we heat our cellulose, it is thermally degraded into flammable volatiles, pyrolysis gases, and those are the fuel. And they mix with oxygen in the air, react, and we have the combustion. And this combustion is a chain reaction. So those fragments, the pyrolysis gases that form, they are radical species which have unpaired electrons. So they are very reactive, quickly wants to react with other species, and then new radicals form. So we get the chain reaction where more heat and fuel is formed and the fire develops rapidly. So a flame retardant can delay or prevent the fire by removing one or several of those components. And fires take many lives each year. Only in Sweden, 100 lives are lost. But there are also other costs for society: property losses, rescue service, have to clean up after the fire. And there is also, of course, personal suffering. And many of those fires start in loose furnishings, curtains, sofas. So there are requirements from authorities to have a fire-safe built environment. And one way to do this is to use flame retardants. But many of the flame retardants that are used today are toxic. They are made by hazardous reactants, they use hazardous solvents, and they produce hazardous waste. And some of them are also water soluble, so we cannot use them anywhere where they can come in contact with water. So there is a need to replace those toxic flame retardants with non-toxic bio-based alternatives. So that's our project idea: make a flame retardant from non-toxic natural products. So all components we use are found in the food we eat. They can be extracted from waste. We only use water. We mix those ingredients in aqueous solution, and the only byproduct we get is table salt. This flame retardant will make a surface coating that can be insoluble in water, and it will be recyclable, and it will remove all 4 components of a fire. So we have then investigated how good this is on cotton and tried to develop the best possible mixture. So the ingredients we use is ferric acid. It's the natural source of phosphorus. Plants produce this to store phosphorus. So we find it in plants, seeds, grains, etc. We mix it with amino acids, which are the building blocks in proteins. And we also use metal ions, which are abundant in nature, like calcium, for instance. So then we have to find the right proportions to combine all these ingredients to get the best flame retardant properties.
Yeah, hello. I am Anuttam Patra, senior lecturer in Luleå University. I shall talk about experimental part of the project, and that start with sample preparation. We prepared many solutions of flame retardants with varying composition, and the major component was phytic acid. We abbreviate PA. We made 10% solution in water. As Anakarin showed, it is a 6-member carbon ring. Every carbon is connected with a phosphate group, and there are 12 acidic hydrogens in red colors, which means it can react with 12 moles of sodium hydroxide alkali. And for example, if it reacts with 6 mole of sodium hydroxide, then 6 of the 12 hydrogens get replaced, and we call it Na6PA. So if it was 3 moles sodium hydroxide, 3 of the hydrogens get replaced, and we call it Na3PA. So we follow this convention. In our experiment, we added 0 to 16 moles of sodium hydroxide per mole of phytic acid. And when we also used amino acids, it varied from nothing to 4 mole of amino acid per mole of phytic acid. We used pure cotton samples. We cut it into adequate size and then dipped in the solution for 20 seconds, then took it out, hanged in air for at least 1.5 days. And when we wanted to make insoluble films, we prepared multivalent cation solutions, and that we sprayed on these samples and again dried in the air for at least 1.5 days. Now I move to simple combustion test setup that we used. We used a Bunsen burner, which is connected with a propane cylinder. The flame height was always 9 centimeters, which we controlled with the knobs. There is a certain distance between the flame tip and the cloth that is hanged from the top. We used 2 cameras, one in the front and another inside the fume hood, which is connected to a computer. So during the experiment, we can also see the sample from the other side. We checked the temperature variation over distances. So from the flame tip to 10 centimeter distance, and the temperature was measured with a thermocouple 0.25 millimeter thick. When the distance between the flame tip and the measurement was 10 centimeters, the temperature was 200 degrees. So if we hang a cloth, I am showing you the differential thermogram for both untreated blank cotton and also one of our flame retardant treated cotton. At 200 degrees, both has no effect. So if we plot, you can see there is no change. If we bring the cloth closer to the flame tip, 7 centimeters from the bottom, the temperature rises to 300 degrees, which is at the onset of the decomposition temperature of the treated cloth. So in the graph, it decreased a little bit, but the untreated cloth is not affected. When the distance is even lesser, 5 centimeters, then the temperature reaches 350 degrees, which is just above the decomposition temperature of the treated cloth. Then we see little more change, but the untreated pure cotton, there is no weight change. However, when it is much closer, like 3 centimeters, temperature is close to 460 degrees. And that is higher than the decomposition temperature of the pure cotton. Then that catch fire and burns completely. And you can see the weight become close to 0 or just 10% remaining. And when we move closer and closer to the flame, the untreated cloth, similar way, it burns, but the treated cloth, there is only a very little decrease in weight. They never caught fire, or even if it caught fire, it self-extinguished in all cases. Thus, 3 centimeter looks a bit black because I exposed it for a bit longer, like 5 minutes, to check what happens, but other ones are just for 1 minute. Otherwise, it will be a clear trend. Now I show cone calorimeter test. This is where we stopped actually in the last project, our first project with Brandforsk. We used blank cloth, Na6Pa and Na12Pa, and result was promising. For example, with Na6Pa, the total heat release, THR, was lesser. So we wanted to explore it more. We prepared also PA, Na3Pa, of course, Na6Pa, 9, 12, and 16. And it was interesting to find PA and Na3Pa, the heat release rate, HRR, is much lower. And if we see FIGRA index, which is the ratio between the maximum for one sample, HRR maximum, HRR at one sample, divided by the time it took to reach that maximum, we see HRR FIGRA index increase almost linearly with increasing number of sodium ions. And also we saw the clothes burns more and more with increasing number of sodium, because we can measure, we can see more carbon dioxide is produced. And that we measured by analyzing the evolved gas from the cone calorimeter with an FTIR spectrophotometer. It happens because when we replace the acidic proton with sodium ions, there are less acidity. So the cotton cloth get less charred, and less charring cause more burning. So that way, PA is, you can feel that's really good, but it is very acidic. So our choice is Na3Pa, which is much less corrosive, more neutral, but still very good as a flame retardant. So that is the basic choice of our sodium and phytic acid. So now we move to the next step, which is the actual goal for the project in composition wise, to try amino acids. We used different amino acids, but first interesting thing we saw, now these flame retardants can actually tolerate much higher heat flask. Here we can put 20 kilowatt or more. In the previous one, if we increase more than 14.9 or 15, even the flame retardant treated clothes was burning too fast. But this one can withstand much higher heat flask. If you put a normal untreated cloth, it will be very high, more than 200 kilowatt per meter square in HRR value. But when you have amino acid, it decreases a lot. Especially one amino acid called arginine, that shows very interesting result. The HRR decreases very much, and not only that, the peak comes very late. It makes the FIGRA index very low. Remember, the lower the FIGRA index is, the better the flame retardant. So arginine is the best amino acid among the things we have chosen. We have tested a lot of amino acids and even their mixture, but arginine is definitely the best. The samples we made with arginine, there's always self-extinguish if it catches fire, but most of the cases, they don't even catch fire. So now we wanted to check how much arginine is best. What is the ratio between phytic acid and arginine to get the best result? When we put very little, 0.3 mole of arginine, we already started seeing very nice flame retardant behavior. It can withstand 20 kilowatt. Without arginine, of course, as I told, we cannot put this high heat flask. It will burn, it caught fire immediately. But when we increase to 0.7 to 1, then wow, it's really low. So that is the best range in the FIGRA index. But when we are increasing arginine more, we can see the HRR is coming a bit fast. At the peak of the maximum, it comes a bit early and the peak is increasing. So in those cases, the FIGRA index increases again. So 0.7 to 1 range, we have the best flame retardant behavior with arginine. That is really good, but there is one inherent problem. These are sodium salts. And you know, monovalent ions like sodium, potassium, ammonium, they are always water soluble. And these ones are no exception. So although this flame retardant is good, we can use this where there is no water exposure, like inside the building material. But if you put it outside a building, if there is a rain, it will be washed away. If you use on a cloth and do the washing, you will lose all flame retardants. So we need insoluble flame retardants. We used multivalent metal ions because their water solubility is much less, like calcium and aluminium. And you can see they are still quite good, especially aluminium. The FIGRA index is very comparable with the sodium salt. And in this case also, the samples can self-extinguish if it caught fire, or most of the cases there was no fire observed when they were exposed to flame. We also tested all the samples with thermogravimetric analysis. I will not show all, but for this, our final mixture, I will show. For the black one, the untreated cotton, it can withstand heat quite high. At the beginning, till 350, there is nothing, but then it catches fire and it loses almost all the material. Above 550 degrees, it's almost gone. At 370, almost 85 to 90% is gone, but at the same temperature, the treated clothes lose around only 40% of the weight. So that is good. And also for these calcium and aluminium samples, they started decomposing at 200 degrees, a bit lower. So the flame retardant behavior already started at that temperature. So that is also quite impressive.
Yes, thank you. So all those thermal analyses that we did gave us some idea how the flame retardant works, but what is happening on the chemical scale, if we go into the molecules and see how they change at different temperatures, then we can use a method called nuclear magnetic resonance to look at this. So we took samples of our pure flame retardants, no cotton here, only the flame retardant, and we heated them in a furnace to different temperatures and analyzed those peaks that you can see. So this is carbon. So what is happening with the carbon part of the flame retardant? Unfortunately, some of the samples were too viscous, so we couldn't analyze them properly. We will increase our efforts to try to get spectra of those as well. But so far, if we look at the sodium version, the soluble one, which only contains sodium, arginine, and ferric acid, then we couldn't see anything below 400 because of this viscosity. But at 400 degrees, we can see that there is one peak, which is a sign of polyaromatic char. So somewhere at a temperature below 400 degrees, we know that this flame retardant has converted into a char. And at 600 degrees, there is no signal left. So this char has now decomposed, burned, probably. If we add calcium ions to make it insoluble, then we can see at 200 degrees we have a spectrum, but not at room temperature. So the large peak at 200, that comes from the ferric acid, and the 5 small peaks are from the arginine part of this flame retardant. So we can see at 200 degrees it is still intact, more or less. We can see that we have both arginine and ferric acid. But at 400, all those peaks are gone, and instead we see this peak from the polyaromatic char. So again, sometime between 200 and 400 degrees, our flame retardant starts to decompose and make its flame retarding effect. And at 600 degrees, this char is also combusted. When we have aluminium instead of calcium, then we could see everything from room temperature and up. So at room temperature, we see the big peak from the carbons in the ferric acid and 5 very small peaks from the arginine. At 200 degrees, the ferric acid peak has decreased. So that's why the 5 arginine peaks look much bigger. So we can see that the ferric acid starts to degrade into some gaseous fragments that disappear from the system already at 200 degrees. And we saw from the TGA measurements that already at 200 degrees, the flame retardant starts to lose mass. The arginine is still intact because arginine is more stable thermally than the ferric acid, so it doesn't start to degrade until maybe around 250. But at 400, everything is decomposed and we only have a char left. So this ferric acid is transformed into a char. And in this case, the char is also stable. So at 600 degrees, we can still see a lot of char left. We can see that those gases that form when the ferric acid and arginine is breaking down between 200 and 400 degrees, those gases can intumesce the char that is forming. So you can see the figures there, photos of the flame retardant at this 400 degrees from the furnace. So you can see there is an increase in volume, especially for the sodium version, but also when calcium and aluminium is added to the system, we can see a volume increase compared to the original sample. If we look at the phosphorus part of our flame retardant, then again, we don't have any spectra to show for sodium below 400 and calcium before 200. But those peaks that are marked with a star, they are no real peaks. They are just spinning sidebands that appear from this experimental technique. But there are 3 peaks visible at 400 degrees for sodium, and they come from sodium phosphate and from polymerized phosphates. So sometime at a temperature below 400 degrees, the ferric acid phosphates will form a polymer. If we look at the calcium, then we have spectrum already at 200, and we can see from this spectrum that some part of the polyphosphate groups have started to polymerize, but then the amount and degree of polymerization is increasing at 400 degrees. So then we have one more peak furthest to the right. And at 600 degrees, this sample has become much more crystalline. So we see many, many sharp peaks at that temperature. Aluminium is a bit of a problem because the signal from aluminium phosphate is in the same region as we expect peaks from polymerized phosphate. So we cannot really say if the aluminium version of our flame retardant also polymerizes, or if it's just forming phosphate, or if it's a mixture, but probably it is a mixture. So with all this information, we can now explain what exactly is happening step by step with our flame retardant. So the first thing that happens between 200 and 300 degrees is that this heat will thermally degrade our flame retardant surface coating. So we will then remove heat because it's needed for this degrading. So the phytic acid will form phosphate groups and this cyclic carbon ring. The amino acid, then depending on which amino acid we have, different types of decomposition products can form. But one thing that is common for all amino acids is that we get CO2 and ammonia. And then in the next step, we will remove the fuel. So those acidic phosphate groups that have formed, it will be like phosphoric acid, they will char the cellulose. And then that will decrease the amount of pyrolysis gases forming, because instead of decomposing the cotton into pyrolysis gases, instead we form this char. But there will still be some pyrolysis gases forming, but since this charring starts at the low temperature, the composition of the pyrolysis gases will be different than if this decomposition takes place at 370 degrees. So that this composition then will also minimize the risk of fire because they will be less ignitable. Then we will remove some heat again, because those phosphate groups then above 200 degrees, they will start to polymerize, and that requires some heat. We will also have those cyclic hydrocarbon rings from the phytic acid. They will fuse together and form this polyaromatic char. And together with the gases that also forms CO2, ammonia, that are non-combustible, they will intumesce this charred layer. So it will then start below 300 that we will get this intumescent layer as well. And this will prevent the heat transfer when it's formed. We will also remove the oxygen. So those non-combustible gases formed when the mainly amino acid is decomposed, the ammonia and the CO2, they will mix with the oxygen in the air so that the oxygen will be diluted. So it will have so low concentration that it will be difficult to ignite the pyrolysis gases that still are there. And this starts below 300. And this intumescent layer that is formed, the polymerized phosphate, which is a kind of glassy material, and the third component, the metal phosphates that form, which are enamel-like calcium phosphate is the same mineral as we have in our teeth enamel. So all those will form a barrier that will also prevent the oxygen from coming in contact with the fuel. And this happens also between 200 and 400 degrees. So all of those mechanisms are relevant before the natural thermal degrading temperature of cellulose. We can also remove the chain reaction. So if you remember, this bond breaking from the pyrolysis forms those reactive radicals with unpaired electrons, which then wants to react quickly to pair the electrons, and then we get the chain reaction. But sodium and phosphorus are known to be radical inhibitors, so they can terminate those radical reactions, so that will reduce the rate of the combustion reaction. So then our final part, to see the solubility. So we did some leaching tests. We took a piece of our cotton treated with flame retardant, put it in water, and then at regular intervals, we took out a sample of this water to see how much of the flame retardant has dissolved into the water. So the upper curve there, the red and the black one, shows when we have our soluble flame retardants. And the blue and green at the bottom are the more insoluble versions with calcium and aluminium. So we can see that much less of the flame retardant is dissolved when we have calcium and aluminium ions in the system. Both the ferric acid and amino acid part stays on the cotton to a higher extent. So the conclusions we can draw is that the results from the different analytical methods that we have used agree with each other. The macroscopic fire properties can be linked to the molecular properties of the flame retardant. If we have compositions with ferric acid, amino acid, and metal ions, they are better than if we have compositions with only two of the components. Arginine is the amino acid which gives the best result, and cotton samples self-extinguish. The flame retardant mechanisms attack all four sides of the fire tetrahedron, and when we add the multivalent metal ions, we can reduce the solubility of the coating. So thank you for listening.
Thank you very much, Anna-Karin and Anitam. First question here is this a product that we can see in the market?
That's not so easy to say. We still have some more tests to do because we have only worked in lab scale so far, so we would need to go to a bigger scale and do standard tests and so on. And the product maybe need to fulfill other criteria as well, not only prevent from fire. So that is also left to try. But we know that there is some interest from the market, so hopefully it will be available, but maybe not tomorrow.
Yeah, but hopefully in the future. Yeah. And another question here: did you try higher heat fluxes than 20 kilowatts in the cone calorimeter?
This one I can take. Yes, we tried. But most of these cotton pieces were very normal, thin cotton. So some cases they caught fire a bit faster than. So to have a more reproducible result, we have chosen 20 kilowatt. That is the answer. But of course, I saw it can withstand the heat. And that will be the next step maybe. We are started working with thicker clothes and maybe on woods. We'll then see higher heat flux in same retardants.
Yeah. Because you have more steps in the future, and you will try more things. And did you try any cone tests after your leaching studies?
No, but we tried actually burning test, and there it was still good. So that may be another thing we can do. We can do cone test, but I put in water for some time, take it out, dry it again, and hang it below a flame. Sorry, over a flame.
Yeah.
And it did not catch. It was quite similar. So of course, with the multivalent metal treated or insoluble film cases. You want to add something, Anna-Karin?
No, that's okay.
Yeah. But of course, as you can expect, the soluble ones, they dissolve quite a lot. So they are not good after this water treatment. But they can, if you ask about times, we hanged it for like 1 year old and they are still good. There was no problem, no decomposition. So I prepared sample 1 year back and kept it in the air for 1 year.
Okay.
So room moisture didn't, or no other problems.
Excellent. That's very interesting. Have you performed any standardized tests for fire rating, for example?
No, not yet.
Not yet. No. And
that is interesting to do.
yeah. We also have a question here about the source of the amino acid, for example, and or the other chemicals that you use, the phytic acid. How can you get hold of these?
Well, they are parts of the proteins, so we can simply degrade proteins and get the amino acids. And there are also ways to I don't know how much we can say about other projects that are available to produce those by bacteria and that can produce some of those.
At present, we are buying commercial sources. And since it's in the lab scale, it's like standard, like Sigma Aldrich or Mark, we are purchasing. But as Anna-Karin told, there are people do research, or there are some established method of producing both. And of course, it's part of the plan to combine all, starting from the basics, production of these from waste material, so that it's like a total environment friendly project from starting material to the product.
Yeah.
And since we are chemists, it's quite within our range, so that I can confidently tell. And we know who are also working in this, so we can make a bigger consortium in terms. But first, me and Anna-Karin want to make the process to be more clearer instead of going for the secondary step.
Yeah. So when I mean, you claim that this is environmentally friendly, that can you, all the things that you use, sodium, calcium, aluminium, phosphor, phytic acid, and arginine, are they all environmentally friendly? And
yes, we take them from, since the idea is that all of those products should also be taken from waste. So like phosphates, they can cause eutrophication if there is too much runoff into seas and waters, which can be a problem in the manure from poultry farms and pig farms. But if we take this material from there and use it as a flame retardant, we will minimize this. And since we plan to have a very insoluble product, there will be no leaching from our product. So there will be no phosphates going back out in nature. And amino acids are edible, and this phytic acid is also part of the food. So when we eat our muesli for breakfast, we have those seeds and grains and nuts, and then we eat those phytic acid molecules bonded with calcium and other metallites.
right.
So it is part of our common foods. Like I hope you all had this during our breakfast, all this material, knowing or without knowing.
That's good. Yeah, that's very good. So far, you've been working with textiles, and do you have any plans for wood, for example?
Hopefully, that will be the next step. We have some tests that some of our students did a few years back on wood, but there are many experimental difficulties with wood compared to cotton. So then we decided to focus on cotton just to see how the flame retardant works. And now we are ready to take on with the wood.
Yeah, that's very good. Have you considered when I mean, if you use this for fabrics, for example, in your home, let's say on your couch or your clothes, and many people that get injured or killed in fires, the fire begins very close to the victim, and in this case, if you have treated the fabric, it may produce some fumes in the early stage where your flame retardant will react. Have you looked or think about if there is any toxicity in those fumes that can affect the person?
Anatan? Do you want to reply?
We did started analyzing the evolved gas. We have established our one FTIR spectrometer that our university had for many years but never used, but now I set it up. So that work we are doing, and we'll do it more.
Yeah,
But what is expected is that we will get some ammonia and some carbon dioxide.
Yeah.
So not enough to poison anyone, but maybe depending on how much it is, because we see that they self-extinguish even if they are very close to the flame. So hopefully there will not be very much of those gases released at all before everything stops.
And I did not see any carbon monoxide peak in FTIR. At least that's what makes me quite happy. Because carbon dioxide is not something that kills. It just chokes a bit, but if you come out, it's no problem in few minutes.
Yeah. We have a long question here. I will read for you. Well, first of all, it says the person says excellent presentation and looks promising to replacing, for example, PFAS compounds that have been used in the past. Are you going to do toxicity testing to demonstrate if the product or byproduct following a fire is released to the environment? If it will cause any harm to the environment, for example?
We haven't done that yet, and of course that's something that has to be proven, I guess, before the market will be interested. So definitely we are interested in doing such tests.
Yeah.
And product should not be toxic. Even the byproduct that forms to produce them. That was be also very careful. No intermediate is toxic. That final product does not make much sense, to me at least, to have toxic intermediates and have a final good product. And the final, during the gas, that we have to test when its cause or what products it forms. But again, the positive side we are doing, the NMR things that Anakarin showed, that we also identify the product from chemist point of view. So we'll know what exactly you form. One thing they will tell how much heat product there, so we can control how much heat production happens after or during burning. But we can also identify what happens. So that's a strong side for us.
Yes, and you have some work ahead of you, and of course, and to learn more about the chemistry and try to find a product. And you also have submitted a patent for this on your journey towards a product. So what is next now in your research? That I know that you will move on, and I think also speed up in your work. Can you tell us about it?
We have recruited a postdoc who will start in January. So then we will have more hands in the lab. So then we can speed up a bit and hopefully get many more exciting results. So our plans is to continue with all those questions that are still remaining when it comes to cotton. But we will also start to do some investigations on wood.
Yeah, that's really interesting to see. We get a question about the char layer. Your polyaromatic char, how stable is that? You did explain some. You showed some tests that you did with different temperatures, and can you tell us more about that?
As we could see when we have the aluminium in the mixture, then the char was very stable. So it was a lot of char left already at 600 degrees. And 400 for calcium and sodium, it was gone at that temperature. But we haven't analyzed in more details. We cannot say now exactly what it is that makes the char more stable when we have aluminium. It's probably how those aluminium phosphates and polyphosphates mix with this char.
Right. So it depends on your what metals that you use.
Yeah.
A question: how many % of flame retardant did you add to the cotton?
It's around 10%. We tried from 1 to 10, but I'll also try to decrease it little more. That is one of the plans. But presently, mostly we done 10%, and that is what we reported in the Brandforsk report. So, which I think will be published soon in the website.
Yes, we will.
Yeah. So it is 10. Straightforward, it's mostly 10% that the result we showed in the presentation. 10% of the phytic acid, of course, and then others are related to that.
This is someone that has a building product with high environmental focus that might benefit from a product like this, and want to seek some contact with you to see if they can use that in their projects. We will see to that.
Yeah, and anyone who is interested in contacting us are free to do so, and we are happy to find people to collaborate with who can contribute with other knowledge than what we have.
Yeah, that's very good. Okay, thank you very much. Really interesting. I'm looking forward to the continuation of your research, and hopefully we will see products in the future that will help us. I think this can be a great contribution to help people from not getting injured or killed in fires. So thank you very much. I will just wrap things up here and give some information about our webinars in the next few weeks as well. So thank you, Anna-Karin. Thank you, Anatan.
Yeah.
Thank you.
So, and thank you for all your questions and your interest. If you want to attend more Brandforsk webinars, we have 2 more coming up this year, and you can find them on our webpage. And the first one is about ITM data exchange, and that will be in English. And the second one is about fire safety for buildings with cultural values, and that will be in Swedish. You can, if you want to have our newsletter, you can find that in the bottom part of our webpage. And if you have missed any of our earlier webinars, you can find them on our YouTube channel, and also some recorded seminars before we began with webinars as well. And before we close, I would like to thank Anna-Karin and Anatan again, of course, and also all of you that have contributed with very interesting questions. And also thank you, Francis and Matthias, that have been producing this webinar. And of course, a great thank to all our supporting organizations that make this possible. And also, of course, feel free to get in touch with us. You can find our contact information on our website. Thank you. Bye-bye.